Hey, how's it going? I'm about to do a Codeforces round. It's round 1062, it's a Div 4, and I'm very rusty, so let's see how we do. Alright, we're actually in right away. Form a square. What does that mean? Are they all equal? Oh my god, that's it. I'm not even going to compile it. Right, well I guess I do. Oh, okay, got it. Why do I need n? Alright. If they're different. Like if they're different pairings, so as long as there's one of each, you can sort them, and then if there's not, you can't sort them. That sounds right. I'll just do this. Vector. Oh, I don't know. Alright, next time. Yet another array problem. X such that I with GCD. What is GCD scalar? Oh, find the smallest number that's relatively prime to something? You can just iterate because it can't be that many. I mean, I guess we can like go through prime. I don't know if we even needed the prime check, but sure. Two zeros. is not to do. K teleports. Each one to the nearest teleport. So X, what does this mean? K teleportations that are just maximum. Oh. N and K. N is number for number teleports, and X. I see it's at least big enough. Okay, and then the position of the friends. Distinct. Okay, so I think you just binary search, and then you count how many things are far enough. So it's a little tricky actually. I'll just do this to be safe. Okay, and now that means low, otherwise high equals -1, which means go to this. This can be an insistable, I guess. Okay, so 0, right. So minus 2 times d plus 1. Yeah. So if they're 2d apart, then there's 1. Yeah, okay. And then what is it? X minus 8 up back. Minus d plus 1 again. And then we're going to up it low. Oh, what? Oh, I need to, what? I need to output the positions? Come on, man. Okay, so 0, 2, 1, 3. Yeah, okay, so that's correct. I just need to. Wait, what? Fine, set. Okay. This is fine. I got Cloudflare. Okay, but I got this mission. It's kind of hard. Is this AI solved or is this real solved? No drops. She wants to sort it. What? Why are we doing all this? Just say we want it to be sorted. Okay, so we keep some the same, and then so the ones that we keep need to be sorted. Right? Am I understanding that correctly? Yeah, and CI, 0 and 0, and this is 3. Right. So maybe 2. Right. Yeah, okay. I'm confused. Is that it? Surely you can do this even better, but I'm very confused. What is going on? Why is this the thing? This is like, it's like kind of computing LS. Okay, and then the tree. Okay, so how many things can be the LCA? It's just how many things have a subtree? How many things have a subtree of size at least k? Yeah, that's it. So for every edge, got it. Okay. I mean, straightforward at least. Should probably check this to see if it happened. Does it want to show me anymore? Okay, so now what are we doing? We are going to see there's also the self root, which everyone satisfies. So now we're no longer counting self roots. I don't know, maybe that's if also got subtree size, no, it is okay. And minus if n minus L2 got subtree size, okay, then and I think that's it. Oh, what happened? Oh. Really? That's it? That's really it. Oh, wow, E took me the longest. What was E? All right, so we got a pretty clean first place here. And yeah, now I'm just gonna go through the problems pretty quick, just go through the ideas. Cool, so problem A, you get 4 numbers, check if you can make a square. It's just, are all 4 numbers equal? So print yes, otherwise print no. That's it. Problem B, you want to know if you can rearrange the letters of one name to be the letters of another name. The key idea here is you just sort both the strings and then they should be equal. And that's it. Problem C, you can swap and you want to sort the lists as much as you can. You want to make the lexicographically smallest list you can make. You can only swap two numbers if they have different parity. So one is even and the other is odd. So it turns out, as long as you have at least one even number and one odd number, you can just make any swaps you want to make. You can think about picking one like special number and just swapping around all the other numbers of the other parity, and then kind of vice versa. It takes a bit of thinking, but you can convince yourself of this. And so, as long as you have both of them present, you can just sort the thing. And if you only have one parity, you actually can't do anything. So you just output the list, as is, for example, this case. So that's C. D. Yeah, you want to find the smallest number that is relatively prime with one of the numbers in the list. So first of all, this number is going to be a prime, because if you end up with an answer that's not a prime, you could have taken a prime factor of it instead. So we just need to check primes. And the other observation is the answer is not going to be very big, because in order for the answer to be very big, then every number in the list has to be divisible by every prime underneath that answer. And that will blow up exponentially, and so these numbers will get too big. And so given this, I mean, I didn't actually multiply, but like, 2 times 3 times 5 times 7 times 11, you keep going. At some point, it'll exceed 10 to the 18th pretty quickly. The answer can't be much more than that. So I actually just coded this. I have a function to check if everything in our array is divisible by number x, and I just increment p. I'm looking for a prime that's not that not everything is divisible by, and then that's the answer. Cool. So that's D. All right. So here's E. E was actually, if not maybe not the hardest, but the most time-consuming of this problem set. So you have n friends, they're each in a position, and you have a range. You just have a single line. They're each in a range 0 to x, and you want to add k teleporters to maximize how far any of your friends is to their closest teleporter. You want to maximize the distance for the closest friend. So this is a very standard binary search approach. And so what I did here is I do a binary search to find the distance, the largest distance that still gives us at least k spots to place teleporters. Because once you decide your distance, then you know like exactly where you can place teleporters. Because if you have two consecutive friends in the list, you need to make sure you're like in a certain range to be far enough from both of them. And then the very left friend and the very right friend are two edge cases. Literally edge cases. And so you can just go through and count pretty quickly. And then the tricky thing is you have to output, you don't output the distance, you output the positions. And so I have some logic here. This takes care of things to the left of the first friend. This takes care of things in between two friends, and this takes care of spots to the right of the last friend. And then you'll notice I have this logic on all of them. Positions.size has to be less than k to keep going. And the reason for that is, first of all, we only want k outputs, but second of all, if otherwise, if you end up in a situation where you add too many positions, you could run out of time. Although maybe that's not an issue given that we just did this binary search. I didn't really think about that, so I don't know. I just did that to be safe. That's E. Cool. So F. So the key idea here is you want to know whether a node can be a lowest common ancestor of k distinct nodes of a tree at some root. So the key idea here is a node can be an LC of k distinct nodes if and only if its subtree has at least k nodes, because you can just, if it does have that, you can just pick all the k nodes in the subtree, and if it doesn't have that many, then any set of k will include something outside of the subtree, so you can't do it. So we're really just looking at subtree sizes, and so the tricky thing about the rooting is that subtrees can like go one way or the other way. The way to think about this is if you have any edge, an edge basically creates two subtrees, one that goes down and one that goes up, and you should look at both of them. And the idea is for a particular subtree, if its size is at least k, then you end up adding to the answer the number of roots, which is actually in the opposite subtree. And so that's the logic here. So that's all boilerplate code, but this builds a tree, and then every node works with itself as a root, so we're counting that first. And then otherwise we're iterating every edge. So we skip node 0 because node 0 doesn't have an upward edge. And then we just do this logic that I mentioned for both subtrees, that this is the down subtree and the up subtree. All right, so that's F. And then G, this one was quite weird. It was a very easy G. You have an array and you can pick some of the positions and replace them with any number for a certain cost dependent on which position it is. The ones you don't change, keep the values. And then I don't know why they said this, but the point is you want to make an array that is sorted in ascending order, or like non-descending order. And so instead of focusing on which ones we change, we should actually focus on which ones we keep. And we should view it as like how much can we save by keeping certain positions. And then you'll realize this is basically like an LIS problem, longest increasing subsequence. It's a weighted LIS essentially, and so you can just, I don't know why they made it only 8,000. You can just code the quadratic DP very simply, just like this. But if you want, you can even improve this to an n log n using some simple data structure, Fenwick tree, something like that. I also compress the array for convenience, but this is the idea here, and this is n log n, and that's it. So that's G. So overall, I think relatively easy div 4, but a nice quick one. And yeah, it's been a while, but good to see everyone. So hopefully, I'll be able to make a few more videos every so often, but we'll see. But anyway, thanks for checking in, and see you in the next one.